Chapter 8, Quasi-experimental research. According to the dictionary, the prefix quasi or quasi means resembling or apparently but not really. So, quasi-experimental research refers to a kind of research that resembles true experimental research but not entirely. While independent variables are manipulated in this design, it lacks the random assignment seen in true between groups experiments and does not include counterbalancing as a true within subjects design would. Additionally, a control group may be absent in quasi-experimental studies. Since independent variables are manipulated in a quasi-experimental study, there is no issue of directionality like in correlational research. This is a clear advantage for quasi-experimental research. However, because there is no counterbalancing or random assignment, the design cannot fully control for confounding variables, which is a drawback. Although internal validity is greater than in non-experimental studies because independent variables are manipulated, it remains lower than in true experimental research due to the absence of random assignment or counterbalancing. So, quasi-experimental research design is useful when researchers want to examine the impact of an independent variable, but cannot use random assignment or counterbalancing. This approach is frequently employed to assess the effectiveness of psychotherapy or educational programs. In this chapter, we will explore some of the most widely used quasi-experimental research designs. All right, the first section, 38, one-group designs. In a one-group post-test only design, a treatment or an independent variable is implemented, followed by the measurement of a dependent variable. Plus, this design lacks a control or comparison group, which is why it is called a one-group post-test only design. For instance, consider a researcher interested in assessing the impact of an anti-drug education program on elementary school students' attitudes toward illegal drugs. The researcher could implement the program and then promptly measure students' attitude after the program concludes. This design is the weakest form of quasi-experimental design. Its primary limitation is the lack of a control or a comparison group, making it impossible to determine what students' attitudes would have been without the anti-drug program. Despite this significant flaw, the results from this design are often highlighted not just in the mainstream media, but also on social media and can be misunderstood by the public. For instance, this Swedish mom truly believes sugar makes kids hyperactive, and she believes her one group post test only design worked. BBC News reports her case in an article. A Swedish mother's successful stand against sugar has turned her into a social media sensation. Anna Larsson decided to cut out sweet treats after realizing how bad her young daughter's cravings had become. The result shocked her. After a difficult few days, the little girl was no longer asking for yogurts and iced buns, but happily consumed healthy options she would once have rejected. What's more, she was sleeping better and was less grumpy. Amazed, Mrs. Larson, 38 years old, shared her experience on Facebook in a post which has since been liked more than 2,400 times. Now, this story is very cute and all, but unfortunately, there is no scientific data to support her claim that sugar intake causes behavior issues. This is probably more a result of illusory correlation or confirmation bias, meaning she selectively focuses on things that make sense to her and ignores the rest of ignores the rest to confirm her own hypothesis. It's also possible that her daughter's taste changed as she grew up. None of these speculations, including Mrs. Larson's own conclusion, can be confirmed because she did not have a comparison group. Okay. Here is another example I found. In 2020, Essence, an online magazine, I believe, published an article titled Black Women Are Using Vicks Vapor Rub on Their Edges and Hair to Make It Grow. Does it work? One of the examples cited in the article is a YouTuber who reads comments from her fans on YouTube. They claim Vapor Rub works as a pimple treatment, mosquito repellent, or first degree burns, itchy relief, sore muscles relief, eczema relief, and even for hair growth and anxiety relief. She treats these comments as if they are facts. She even stated in her video that it's not just me saying, but people saying Vapor Rub works. So her logic is that if many people say it, it must be true. But of course, she is making a decision based on anecdotes and has no comparison group to test her hypothesis. This is really poor way to determine facts. Let's say that you cannot include a comparison group, but you want to test the effect of an independent variable. One way to improve the one group post-test only design in that situation is to add another dependent variable. In a one group pretest post-test design, the dependent variable is measured once before the treatment is implemented and once after it is implemented. For example, just like the Swedish mom we discussed in a few slides ago, you might also think that sugar causes behavior problems, which doesn't. But so if you drink too many sugary drinks, it can increase rambunctious behaviors in kids. Although it's a myth and there is no scientific data to support this idea, let's say you want to find out if that's true with a better design than a one group post-test design. In your study, you recruited a group of kids at the campsite. After measuring their rambunctious behaviors, you asked them to reduce their sugar intake. You did this systematically, so you are very confident they decreased their sugar consumption. You then measured the same behaviors later and found that the target behavior score actually declined. Therefore, you celebrate that your hypothesis was correct, and that concludes the story. Of course, if the average post-test score changed compared to the average pre-test score, then it makes sense to conclude that the treatment might be responsible for the improvement. However, like the one group post-test design, there are several alternative explanations because there is no comparison group. As shown in the previous slides, relying on a single group often prevents you from drawing firm conclusions since other factors might explain the changes in post-test scores. These alternative explanations threaten the internal validity of your findings. The first one is history threat. This is one of the alternative explanation. These threats, the history threats, result when some external or historical event affects most members of the treatment group at the same time as the treatment. So it's unclear whether the change in the dependent variable for the experimental group was the result of the treatment or the result of the historical factor. For example, imagine that you were collecting data from participants in the United States for the effect of yoga on depression, without comparison group during the COVID pandemic. And the vaccination was still under development. You may find no effect of yoga, but that may not be because it does not have an effect, but because people were stressed out due to the pandemic. How can we prevent that history threat? To deal with this threat, researchers can add a comparison group. If both a quasi-experimental group and a control group showed similar dependent variable, then they could conclude that the independent variable did not have an effect. But if they found a difference in dependent variable, they could conclude that it is due to both the effect of history and the dependent variable. Maturation threat is a change in behavior that emerges spontaneously over time. For example, Mrs. Larson's daughter's behavior and her choice of food improved after the one group post-test research, probably because her daughter simply grew up. Kids also get better and faster at solving addition and subtraction problems as they get older. Maturation occurs not just in kids, but also in grown-ups. Adult individuals tend to get better on their own over time with some psychological disorders. So, how are maturation threats prevented? In a one group design, there is only one group of participants getting the treatment, but in a true experiment, there is a comparison group in order to prevent maturation threats. Therefore, again, adding the comparison group is a solution to this problem. The effect of maturation could be subtracted out when interpreting the results of a study, and a maturation threat can be prevented. Next, testing threat is a form of order effect in a one group pretest post-test design, where participants' scores change because they experience the dependent variable multiple times. Their scores may increase due to practice, called the practice effect, or decrease due to fatigue, known as the fatigue effect. Testing threats impact internal validity because it's unclear whether the treatment caused the change in the dependent variable or if practice or fatigue were responsible. One way to prevent testing threats is to use the post-test only design in which you do not use a pretest. Another approach involves using different versions of the test for the pretest and post-test. Including a comparison group is also beneficial. This allows you to eliminate testing threats since both groups complete the pretest and post-test, but a greater change in the treatment group indicates the effect is likely due to the intervention or independent variable. Instrumentation threat, also known as instrumentation decay, occurs when a measuring instrument changes over time. For example, this threat occurs when observers unconsciously change their observation criteria over time. Another example is when a researcher uses different forms of a test at pretest and post-test, and they are not equivalent forms. To prevent this threat, you can use a post-test only design. However, if you need a pretest post-test design, you should make sure that your pretest and post-test forms are equivalent. When making observations, you might retain the same observers throughout the study. Finally, you might counterbalance the order of the pretest and post-test forms so that some participants receive form A at pretest and others receive form B, and then they switch forms at post-test. You might wonder about the difference between instrumentation threats and testing threats. In an instrumentation threat, the measuring instrument itself changes from time 1 to time 2, while in testing threat, the participants themselves change over time from having been tested before. Regression to the mean refers to the statistical fact that an individual who scores extremely high or extremely low on a variable on one occasion will tend to score less extremely on the next occasion. For example, your 5K running time may be usually good, but sometimes unusually bad. But statistically, your running record eventually settles down and becomes closer to your average pace. So, how can regression threats be prevented? The regression threats can be avoided by including a comparison group and inspecting the results. Regression can be ruled out if there is no difference in pretest between the quasi-experimental group and the comparison group, but there is a difference in post-test. The only reason these two groups are different is because of the independent variable. Um, have you ever made an appointment with the physician because you are sick only to find that you have gotten better before seeing them? This phenomenon, when medical or psychological problems improve without any treatment, is known as spontaneous remission. I had never experienced this issue until I moved to the United States. As in Japan, you can see a specialist on the same day without making an appointment. It's because they have universal healthcare. A group of individuals suffering from severe depression is likely to experience a reduction in average depression levels within 6 months. In a comprehensive review of multiple studies on depression treatments, researchers Michael Posternak and Ivan Miller found that participants in waitlist control group improved by an average of 10 to 15% before receiving any treatment. This example shows why it's important to include a control group in your research study. So, a common way to eliminate threats to internal validity, as discussed in this slide, is to revise the research design to include a control group or comparison group that does not receive the treatment. This control group encounters the same risks from history, maturation, testing, instrumentation, regression to the mean, and spontaneous remission, enabling researchers to determine the true effect of the treatment, if it exists. This highlights the weakness of a one-group design. Therefore, it should only be used when no other options are available. In a classic 1952 article, researcher Hans Eysenck reviewed the results of 24 pre-test, post-test studies showing that about two-thirds of the patients improved between the pre-test and the post-test. But Eysenck also compared these results with archival data from the state hospital and insurance company records showing that similar patients recovered at about the same rate without receiving psychotherapy. This parallel suggested to Eysenck that the improvement that patients showed in the pre-test, post-test studies might be no more than spontaneous remission. Now, it's important to note that he did not claim psychotherapy is ineffective. Rather, he emphasized the need for well-organized, properly conducted experimental studies, true experimental studies. Researchers responded to his proposal by conducting hundreds of experiments where the participants were randomly assigned to a treatment or control groups. These results were summarized in a well-known 1980 book by Mary Lee Smith, Jean Glass, and Thomas Miller. The findings indicated that psychotherapy generally proved quite effective, with roughly 80% of those receiving treatment improving more than the average control participant. Later studies have increasingly examined the specific conditions that influence the effectiveness of various psychotherapy types. Before proceeding to the final section, let's examine a variation of the pretest post-test design known as the interrupted time series design. A time series consists of measurements collected at regular intervals over a period. For instance, a manufacturing company might track its workers' productivity weekly for a year. In an interrupted time series design, this sequence of measurements is interrupted by an intervention or treatment. One classic example of interrupted time series design involves reducing factory work shifts from 10 hours to 8 hours. The productivity quickly improved after the shift reduction and stayed high for several months, leading researchers to conclude that the shorter shift caused the productivity boost. The interrupted time series design resembles the pretest post-test design because it measures the dependent variable both before and after the intervention. However, unlike the simple pretest post-test design, it includes multiple measurements taken both pre and post-treatment. The slides figure displays data from hypothetical interrupted time series study. The dependent variable is the weekly count of student absences in a research methods course. The treatment involves the instructor publicly taking attendance each day, making students, I should say each week, making students aware that their presence of absence is known. The figure indicates a consistently high number of absences before implementing the treatment, representing the baseline. Following the introduction of the treatment, there is an immediate and lasting decrease in absences. All right, next section. This is the last section, 39, non-equivalent groups designs. In a between subjects experiment, random assignment of participants to conditions usually results in groups that are statistically similar to each other, which researchers see as equivalent. However, when participants are not randomly assigned, the groups tend to differ in certain ways, making them non-equivalent. Therefore, a non-equivalent groups design is a between subjects setup where participants are not randomly assigned to conditions. We will explore several types of non-equivalent groups designs in this section. The first type of non-equivalent groups design we will discuss is the post-test only non-equivalent groups design. In this design, one group of participants receives treatment, while a second non-equivalent group does not. These two groups are then compared. For example, a researcher might want to evaluate a new way of teaching the fractions to third graders. One approach would be to have a treatment group consisting of one third grade class and a control group of another third grade class. Note that because third graders are not randomly assigned to a condition, this is a non-equivalent groups design, leading to potential differences between the groups. Researchers using a post-test only non-equivalent groups design can take measures to make their groups as comparable as possible. For instance, they might choose two classes from the same school, ensuring that students have similar scores on a standardized math test and that teachers share characteristics like gender, age, and teaching style. Matching the environment helps improve the study's internal validity by reducing the impact of confounding variables. However, this approach cannot eliminate other significant confounding factors unless students are randomly assigned to conditions, which provides better control over extraneous variables. One way to enhance the post-test only non-equivalent groups design is by including a pretest. In this design, the treatment group takes a pretest, undergoes the treatment, and then takes the post-test. Non-equivalent control group also takes a pretest, but does not receive the treatment and then takes a post-test. The key question is not just whether the treated participants improve, but whether they improve more than those who did not receive the treatment. For example, students at one school take a pretest on their attitudes toward drugs, then participate in an anti-drug program and finally complete a post-test. The students at a similar school also take the pretest and post-test, but do not participate in the program. If students in the treatment group become more negative toward drugs, this change could be due to the treatment, but it might also be caused by external factors like historical events or natural development. To confirm the treatment effect, the treatment group should show more negative attitudes than the control group. If both groups change similarly, factors like the news stories or maturation could be influencing attitudes. However, as you should already be able to guess, this design does not truly eliminate confounding variables. Events such as a student drug overdose at one school but not the other could also influence results. Revisiting the example of assessing a new method for teaching third graders, this study could be enhanced by including a pretest to measure students' understanding of fractions. The differences in scores from the pretest to the post-test would be analyzed and compared between groups to see if one group showed a greater improvement in their knowledge of fractions. Naturally, teachers' teaching styles and classroom environments can vary significantly, potentially leading to different levels of student achievement or motivation unrelated to the teaching intervention. Additionally, differential history presents a risk to internal validity. For example, if asbestos is discovered in a school and it is closed for a month, this disruption in instruction could create differences in post-test scores between groups. If participants in this type of design are randomly assigned to conditions, it transforms into a true between groups experiment instead of a quasi-experiment, which was advocated by Isaac. One way to improve the interrupted time series method is by adding a control group, as you probably have guessed. This involves collecting measurements at regular intervals over time, both before and after an intervention in two or more non-equivalent groups. For instance, the manufacturing company might track workers' weekly productivity for a year before and after reducing shifts from 10 to 8 hours. The study can be enhanced by involving another manufacturing firm that does not change their shift hours, acting as a non-equivalent control group. If the treated group's productivity quickly increases after the shift reduction, while the control group's productivity stays steady, it provides stronger evidence that the treatment is effective. Likewise, an example of examining the effects of taking attendance impact student absences in a course, the design could be enhanced by using students from another section of the same course as a control group. In the treatment group initially shows more absences before the intervention, then a lasting decrease afterward, while the control group maintains consistently high absences throughout the semester. This would offer stronger evidence that the treatment effectively reduces absences. In a pretest post-test design with switching replication, non-equivalent groups first complete a pretest measuring the dependent variable. One group then receives the treatment while the control group does not. Afterwards, the dependent variable is measured again. The control group then receives the treatment, and the dependent variable is measured a final time. For example, to examine the effect of an exercise intervention for depression treatment, we might recruit one group of patients with depression and a non-equivalent control group of students also diagnosed with depression. Both groups initially complete a depression assessment. The patient group then receives an exercise intervention, while the control group does not. Depression levels are reassessed in both groups. We would expect improvements in the patient group compared to the control group. Later, the control group receives the treatment and both groups are assessed once again. A disadvantage of this design is the lack of random assignment, which can affect internal validity. However, including a non-equivalent control group improves external validity. The built-in replication demonstrates treatment efficacy across two different samples, patients and students. Additionally, this design offers better control over history effects, reducing the risk that an external event coincides exactly with the treatment for both groups. For example, if a COVID lockdown affected depression rates, both groups would show the similar change in the rate when measured, minimizing historical confounds. The switching replication also controls maturation and instrumentation effects, as both groups experience similar rates of spontaneous remission, and any changes to measurement tools would affect both groups equally. Potential issues like demand characteristics, placebo effects, and experimental expectancy remain, but can be addressed using the methods discussed in earlier chapters. Okay, this is the last slide. In a simple pretest post-test design with switching replication, the first group receives a treatment while the second group receives the same treatment later, and the initial group continues to receive it. Conversely, in a switching replication with treatment removal, the treatment is taken away from the first group once it has been added to the second group. Suppose we measure depression levels in both groups, patients with depression and students with depression. Then we introduce the exercise intervention, which is the independent variable, only to the patients. After 1 week, we measure depression levels again in both groups. If the intervention is effective, depression should decrease in the patient group, but stay the same in the student group, which has not received the treatment yet. Afterwards, we stop the treatment for the depressed patients and instruct them to cease exercising while the student group begins exercising. After another week of this new setup, we reassess depression levels. If the intervention is effective, depression should decrease in the student group and increase in the patient group since patients are no longer exercising. Showing a treatment effect in two groups over time and observing its reversal after stopping the treatment provides strong evidence for the treatment's effectiveness. This approach not only confirms the reproductivity of the findings, but also helps determine if the treatment effects last even after discontinuation. Discontinuation. Okay, so this is the end of chapter 8.